Okay, so we've talked before about relative extrema or local extrema, and that's just when you have a neighborhood, a little circle in which that person's got nobody bigger than them or nobody smaller. But in the case of absolute extrema, it's all across the graph. So if I have something like this, probably should have made that a little higher. In this situation, you can see that there's no absolute minimum because I keep going down forever in two different directions. But I intended for this one to be a max and for it to be the only one, but maybe it's the same as this one. So when I draw a line across horizontally at that spot, there's no place on the graph above it. That means that it is an absolute max. It could be that these two are both the same, in which case I have still an absolute max of whatever this value is. Let's say this value is 2. Then I have an absolute max of 2, and it occurs at two different places, but it's the absolute max. And again, there is no absolute minimum. But if I restricted the domain, so let's say that instead of just having this go on forever, I made it stop. You get stop there. Then I would have these endpoints. If I have a closed interval continuous function, then there has to be both a max and a min, an absolute max and an absolute min, because I can't keep going forever in any direction. And if it's continuous, then I can't have any kind of asymptotes or anything like that either, or jumps. So if I'm defined on a closed interval, I will have an absolute max and an absolute min. In this case, it looks like the max is here and the min is here. I could have chopped this one a little bit lower, and then the min would have been at the end point. So when I'm looking for where is there going to be a max or a min on a closed interval, so there's a theorem which states if f is continuous on a closed interval, then on that closed interval it will have an absolute max and an absolute min. But it doesn't tell you within the theorem where to find it. It just says there is one. It's called an existence theorem. So we still look the normal places. We still look where the derivative is 0 or undefined. I could have had a pointy place there and it still would have been continuous. So we look for 0 and undefined derivatives, but we also look at the endpoints, because it could be a situation like this where it would have gone on forever if we hadn't kind of stopped it. So here is that definition of absolute max and absolute min. It's the less than or equal to, greater than or equal to, that gives you the possibility of it occurring more than once. But since the maximum value or the minimum value is considered to be the y value, it's not having two maxes or two mins. You have an absolute max, an absolute min at most, but then it can occur in more than one place. So if we look at these graphs, we have this one has the absolute max at an endpoint. This one doesn't have the absolute min at an endpoint. The absolute min is over there. This one, they're both at the endpoints. And here we have an absolute max and an absolute min, neither of which are endpoints. So I'm having to stop every few seconds, kind of pause and restart due to illness remnants, but so the flow is not going to be that great. But okay, so if it's a closed interval, you're guaranteed these things, and the place you look is the critical numbers and the endpoints. Okay, so the first thing we do, we know we're going to check the endpoint. So we're looking for all the places to check. And we'll have -4 and 4 for sure. We're going to take the derivative of this. 3 times 1/3 is 1. And then x squared. Minus 2 times 1/2 is also 1. And then x. And then minus 6. So then we need to factor this. We're looking for where this is 0 or undefined. Because it's a polynomial, it's not undefined anywhere, so we just need to find where it's 0. You can use the quadratic formula here if you're not a fan of factoring. So I get x minus 3 is 0, or x plus 2 is 0. So x is 3, or x is -2. I want to make sure those are in the domain. Sometimes you'll get solutions that aren't in the domain that we're looking at. These both are between -4 and 4, so we have all these to check. And then we would find out what f of each one is. I have decided that I don't want to plug in to these, so I'm going to put this into the calculator, and I want 1/3 x cubed minus 1/2 x squared minus 6x plus 3. I don't really know how to delete. I guess that's how you delete. Okay, so now I'm going to go to table. Okay, so if we look at -4, it looks like -2 1/3. So for -4, I get -2.3 bar. For +4, -7 2/3. For 3, -10.5. And for -2, 10 1/3. So the max should be here. It's the only positive one, and the min is here. We could have seen where to look for it by using the calculator as well. We could go to window and make the x minimum -4 and the x maximum 4. The y minimum, we would have had to guess, but say make it -25 and make the max 25. And then so we would have seen from here that the max is going to happen at -2 and the min was going to happen at 3. So we can now see the shape of the graph. And then we could have just plugged those two in and skipped the -4 and 4 because they were clearly not the max or the min. But it's whatever way, feels more comfortable is fine. I would like you to try to do this one, if you haven't already, with another video. Try to do this one before viewing the next bits. And I'm gonna do it fairly quickly under the assumption that you've already done some work toward it. So go ahead and pause now and try to do this one. So the first thing is you know that those two are possibilities, and then you take the derivative. And then you factor that. And we come up with these possibilities. When you plug these two in, you should get the same number. This one is -7. That one's the easiest one. Okay, I think I've done these correctly. So you should get the max at 6, and you should get the min at 4 and -4. They'll be the same. And hopefully approximately what I've gotten for F. So each of these just got plugged into F. Okay, so if you looked at this, you would have known that the max happens over here at 6, and that the min appears to happen both at 4 and -4. So then you would have had to plug in both 4 and -4 to see which one, and then you would have found they were the same. Okay, so now we have this one. Your first thought might be that this may not be continuous. That would be a reasonable first thought. But x squared plus 2, you'd check over the domain that it was continuous. But x squared plus 2, because that's actually always positive, x squared is always at least 0, so if you add 2, that's always at least 2. Then you don't actually have any place where this is discontinuous. Okay, so we've got for sure to check 0 and 4. And so we have u prime v minus v prime u. So x squared plus 2 minus 2x squared. Again, if we try to set this equal to 0 in the bottom to find where it's undefined, we'll get no results. We'll get imaginary answers. So we're only going to end up looking at when this is 0, so at plus or minus root 2. Okay, so if I plug in 0, I get 0 over 2. If I plug in 4, I get 4 over 18. So 2/9. If I plug in root 2, I get root 2 over 4. And negative root 2, I get negative root 2 over 4. Root 2 is like 1.4. So root 2 over 4 is less than 0.4. It's around 0.35. I guess I could have done that in my head. So this is around 0.35. And this is around negative 0.35. And this is 0.2 bar. So here's our max and here's our min. So the max happens at root 2 and the min happens at negative root 2. Natural log is only defined from 0 to infinity, so we check that domain. The domain's okay. And so we have 1, 4, f prime is 2x minus 8 over x. Remember the natural log x has derivative 1 over x. So this is undefined at 0. You can write 0 right away. And then so multiplying by x on both sides. Plus or minus 2. The only thing is the domain is just 1 to 4. So now we can't use that one and we can't use that one. So we're only looking at 1, 4, and 2. At 1, natural log of 1 is 0. So 1 squared is 1 minus 8 times 0. So that's 1. 4. Natural log of 4 is a little more than 1. I guess we're going to have to put these into calculator. So 1, 4, and 2. So these are our results, which means our max is at 4, and it's this almost 5. And our minimum is at 2, where we have a negative 1.545. Okay, so if it's defined on an open interval instead of a closed one, remember that the reason we couldn't shoot off to infinity is because we had an end point. If it's on an open interval, you don't have to have an end point. You can shoot off like this with these asymptotes. You can have just one or the other. So here we have an absolute min but no max. It could have gone like this and had neither. And here we have an absolute min but no absolute max because of this jump. This is where it's not continuous. So if we're going to look on an open interval for a max or min, then we still find any critical numbers and we still check the values there. But we have to look at the limit because we have no endpoints. So we have to look at, in this case, end behavior. If it's just on an open interval to an asymptote, then we have to look there at the asymptotes as well. So if we look at this, here's a max. If I draw a line across here, there's nothing ever above it. But there is no absolute min because those arrows point down. Here, I can't have an absolute max because that arrow points up, and I can't have an absolute min because that arrow points down. So I just have these local ones. Okay, so here I have one where it's still a restricted domain, but it's an open interval. It's greater than 0, so it's not closed at 0, and it's also going off forever, infinity. So I don't have endpoints, but I have 0 and positive infinity to kind of check the limits. And the derivative, minus 1 plus 9 over x squared. So that's undefined at 0, but 0 is not in the domain anyway. And then I check where it's 0. Oops. So plus or minus 3, but negative 3 is not in my domain, so just 3 I check. Okay, so if I plug in, well, I can't plug in 0, but the limit as I approach 0 is 12 minus 0, and then minus infinity. As I plug in smaller and smaller things to this 9 over x, 9 divided by tiny things is bigger and bigger and bigger and bigger. So I end up with a negative infinity there. As I go off to infinity, I've got 12 minus infinity minus 0. So that's again negative infinity. And then when I plug in 3, I get 12 minus 3 is 9, minus 3 is 6. So it kind of looks like, since my limits are negative infinity on both sides, that I do get to have a max of 6 at 3, but I have no mins. So let's go use a calculator. I'll make my max just something very large. Or not terribly large. I just need to get on the other side of 3. I'll try 10. Okay, so I'm going to negative infinity this way. I'm going to negative infinity this way. That's harder to see. If I change my window, let's make the X max 50. Hopefully that'll be enough to be clearer. So you can see it's going to negative infinity there. So I do have that one max and no mins. Okay, so this ends 6.1, and I will work on 6.2 soon.